What we did earlier was something like this. Now you can see here that we have this electromechanical actuator. Oh, I have one problem. I cannot, if I put this on, I cannot put this. Okay, so let us go back to the PC and let's see if we can make the bond graph here itself. Yeah. So what are we going to do here? So shall I sit down? I think it will be a little easier for me to make the picture. So you can see here that you have the mechanical side, but this time you have got a spring and a damper, and you have got this electromechanical actuator. It's a very common electromechanical actuator which is used for linear actuation, okay, and it could be used in valves. It's also used in your magnetic discs. There are several applications for this kind of actuator. Here we have got a core on which in this core can move, it can slide through this winding. It's somewhat like a solenoid winding, and one can impose voltage, okay. So the voltage can be imposed across the coils of this winding, and the sense of winding has been provided using this cross and dot, okay. So because it's a winding, there is certainly some resistance, winding resistance, and also certain winding inductance associated, and the core is actually connected, one end of it is connected to the spring and the damper, and the other end of the spring damper is connected to the fixed housing, so it is at rest. So depending upon your actuation, the strength of the current, resulting current would result in a suitable force acting on the core or on the head mass, and that would result in motion of this actuator. If you have to draw this, you can start with the electrical side. You can consider a one junction where you have the winding current, and here you can take the voltage that is being applied on it, and here you can assign the inductance using an I element, and also you could assign an R for the winding resistance. Then you have exactly as before, you have the electromechanical effect. So let's say you have, what should you use for the electromechanical effect? A gyrator. Why? Because the relationship has been provided here. You are going to have a relationship between current and effort, which is force. So here you will have a gyrator relationship, and it will produce an output. So here you will have force, and here you have the current. and here you have the mass of the head. So this can be put here. It is capital M. So now we are on the velocity of this head mass, but we still have to model this spring and the damper. So what should we do? We can say that the housing is fixed. So we'll fix it with the help of a source of flow which is equal to 0. And we'll say that the relative motion between this housing and between this mass, that is the relative motion across the ends of the C element of this stiffness and the damper. So that has to be represented. So we could take it as using a 0 element. We will take relative motion. So V minus, don't worry about this, I am taking the arrow directed inwards towards the SE. And here we have a one junction. So this is representing V minus 0. Okay, V is the flow here, 0 is the flow here, and we are having the flow here, which is V itself. And then what should we assign on this one junction? It's a common flow junction. So the velocity here is the same. So what should we place here? Yes, we should place our stiffness and damper elements, and the relative motion across both of them is the same. So we can assign it here itself. So we can assign the C element here and the R element here. Okay. Here, of course, the modulus of this gyrator is mu. This is our bond graph. It's slightly different from the previous bond graph. But now again, you have the question of back EMF. So there will be a back EMF experienced on the electrical side, and this back EMF will be proportional to the velocity of the core or the velocity of the head mass. Okay. So this is how you can model this system. It's a simple model for this system. Here we have an example of a voice coil motor. This example I have taken the book by Benjamin C. Kuo. Actually, this is the same arrangement which is used in discs, in spindle discs, which are used for data storage. And here you have primary and secondary shorted turns, and the principal, the equivalent circuit as given in the book by Kuo is over here. And here you have the bond graph model for it. The bond graph model is almost similar to what we have earlier. There is the electrical side, you are imposing an effort. There is the there is a one junction here. This is the electrical side. This is the armature. This is the current in the armature, or it is the current in this part of your primary circuit. And here you have the inductance, and here you have the resistance corresponding to these two. And then you have you have a branch which is connected here. So this branch, this is a subsystem which has the same flow, and it corresponds actually to this subsystem. So you see that the same current flows through the inductance, it flows through the resistance, so this one junction is okay. Okay? And the same current flows through this subsystem, enters into this subsystem and comes out of it. But inside this subsystem it gets split into two. And that split has been taken care of using the zero junction because it's a current summing junction. So it splits the current, which is the flow, and here you have the this inductance, okay, this inductance here, and you can see that this inductance here, this one, and then in this path you have a current which is shared by, which is common rather, to this resistance and this inductance, and that has been shown here. Okay, so it's the same current provided by this one junction, and here you have RS and here you have I. Here we also have the mechanical side, which is almost exactly similar, except the gyrator I have shown it in two paths, and they have been shown in terms of signal bonds, not in terms of power bonds. Okay, anyway, I am not going to dwell in detail on this. Let's proceed further. Let's take a simple machine tool. Here we have an example of a very common application in mechanical engineering, and perhaps it's also applicable to some extent, slightly modified to textiles as well. Here we have a tool which is mounted on a tool post, and it can be treated as a nut which is just sliding, which is moving, which is having translation because it's in mesh with the lead screw, and this lead screw, as it turns, because the motion of the nut is, because the rotation of the nut is restricted, so you just have translation of the nut, and the lead screw is, you can say, it gets its drive through this motor combination. It may have a gearbox and it may have some coupling over here. So let's see how do we model this. The bond graph model for this coupling, for this system, has been shown here. You have the electrical side. I think you already are familiar with it, so I am not going to talk about it. That is as far as this motor part is concerned. And then you have the rotation of the rotor, the motor rotation. But usually you don't mount motors directly on, you don't mount them directly on the load. You usually have gearboxes, and so I have not indicated it here, but here we have a gearbox, okay, in this part. And so you have a further reduction in the output shaft speed, and that has been shown with the help of this transformer. So here you have the rotor shaft speed provided by this one junction, theta r dot, and you have the moment of inertia of the rotor shaft of the motor, which may be small. And then you have the output shaft of the gearbox, which is directly connected to the lead screw. So it rotates with the same angular motion as that of the lead screw. So we have modeled it using this one junction, which indicates theta dot of the lead screw. And there is a relationship between these two. This is a flow